Okay, yeah, today I will talk about improving explainable AI by Bayesian neural networks. But firstly, I would like to, start with a question. So why do we need explainable AI in the first place? Therefore, let's have a motivating example, which is from the paper Ribeiro from 2016. And so the task is to discriminate between images of wolves and huskies. And so this is a binary classification problem and easy to solve for us. So we train a model with our training images. So we have here the wolves and the labels, the correct labels, and we train our model. So for instance, an SVM or a deep neural network. And the model learns to classify between wolves and huskies. Fine. So now in our test phase, we have this image of a husky and we put it in our model. And the model said it's a wolf. I mean, obviously, it's not a wolf, right? So, and we want to know why the model makes this wrong prediction. So, but when we like to ask the model why, it's just behaved like a black box. So we have no clue why the model decides for the class wolf. And here is where explainability comes into play. So there are explanation methods. For instance, this one here is the LIME method. And we now see which input features, so like let's say which input areas here in the image leads to the classification of the class wolf. And it is like the snow in the background that was responsible for the misclassification. And this experiment was exactly designed like this. So when we go back to the input images, we see, okay, all the wolves had snow in the background. And it was much easier for the model to distinguish between backgrounds instead of distinguishing between the wolves. So it learned like the snow as an important feature. Okay, and this is what we call the selection bias, because like we gave the model just training images which showed the wolf with the background snow, right? So we don't like show like all the scenarios where a wolf is in. This is known as the selection bias of the data. Okay, another motivating example why we need explainable AI is let's have this image of a horse. And we put it in our model. It's a trained model, and the model said it's a horse. Fine, it's working, right? So we take another image like this of an owl, and the model says, again, it's a horse. And it's definitely not a horse. So we wonder why. And then using explainable methods and putting like the prediction back to the model, we will later see how this works. We see now the most important features that leads to the prediction of a class horse, and it was like the text in the image. Okay, and this is why there in the training images we see like here is always some kind of text information in not every image of a horse, but in a lot of the images, and this is why. The model learned also the text information. So this is like the email address of the web page of the photographer and the name, and learned this as a relevant feature for the class horse. So there were like correlations in the training data set with the horse and the text that the model learned. And this is known as the clever Hans effect. So, and this is why because there was this horse in the 20th century known as clever Hans, because it was claimed to solve arithmetic tasks and other intellectual tasks, and it always could, give you the right answer to some kind of task, mathematical task. But later on, it was investigated that this horse does not have any intellectual abilities. It just was responding to the cues of the body language of its owner, so of this man here. So this man here, okay? So the horse wasn't smart, but it could, interpret like the cues of its owner. this is why we called such artifacts clever Hanses. Okay, so in the meanwhile, in the last, let's say, 10 years, a lot of different explanation methods have developed. For instance, just to name a few, like gradient, smooth grad, guided backpropagation, deep Taylor, pattern net, and integrated gradients, LRP. I guess most of you heard at least some of them. And what you can see here, like here's the input feature, here's the explanation of the diverse methods, there's a huge difference. And this is also one of the main challenges of explainable AI, because there's like no real state-of-the-art method so far, because we just have no ground truth explanations. So we cannot really say, okay, this explanation is much better than the other explanation, at least not because we don't have like this ground truth. Okay, so, and I want now to go a bit into the different types of XI methods. And so one of the categories of XI methods are the model-aware methods. So model-aware, just as it says, is like the explanation method knows the model, knows the infrastructure, the different layers, and also the weights and the activation. So it has like just access to the model. We also say sometimes white access, because it's not a black box anymore, it's a white box, and we can compute like the gradient information. So yeah, and what most of this model-aware methods are doing, they have an input image, they compute like the forward path until we get an output. And then we take the output, which we most of the time call relevance, R for relevance, and we backpropagate. So for instance, here, this is the prediction score of the class cat. And we now want to backpropagate this prediction score of the cat to the input image in order to know which features of the input image were the most important for getting this output for the class cat, okay? And this is then distributed, it's depend on the explanation method you use. For instance, the layer-wise relevance propagation, LRP, is a quite famous one. And yeah, it works that it's distributed the relevance in a way by applying some rules such that the sum of the relevances in each layer stays the same. So the sum of the neurons here of the relevances is equal to the output relevance. And so it is distributing regarding the rules until we came to the input image, and there you see, okay, it was indeed the cat that was responsible for the relevance, for the output prediction of the model. Okay, then we have model agnostic methods. So here we don't have this white access to the model. We really just have our black box model. And what we can do here is we can like only change and modify the input image and always query the new predictions the model gives us. So we could, for instance, again, let's assume here that it predicts a class cat here. And we can black out, for instance, areas or blur out or replace them by some random values. And then we can ask the model, okay, how is now the prediction of the class cat? Like, and when in case we black out some parts of the cat, the object cat, then we would assume that the model prediction for the class cat decrease, right? And if we do this a lot, then we would also get some form of heat map where we see then what were the most important areas for the prediction of the class cat. Okay, so now I'm coming to a different category of explainable AI. It's all self-explaining models. So because there is a woman, Cynthia Rodin, a professor from the Duke University, and she claims that we should stop explaining black box models and we should directly develop models that are self-explaining so that you don't really need explainable AI anymore. Okay, and she, for instance, developed the ProFiL, and there we have like a normal CNN, let's say, at the beginning, and then we have a layer where prototypes are learned. So prototypes, you can think about the first step. You learn, like for each class, you learn prototypes from the training data. So for instance, you have this different class of birds here, and then you learn in the first step for each bird's class, like relevant patches of the training data, such that later on the classification is just based on how good your patches of your new test image matches like the learned prototypes of the different classes. Okay, this is why this is also called this looks like that. So in a new image, you just check small patches are looking similar to which patches you learned as prototypes from the different classes, such that your decision is just based on this comparison between prototypes. So, and this is like one of their explanations, where we inserted like also a picture with a clever Hans in it. And this is like the explanation then later on why this horse is classified as a horse. And as you can see, it's not really precise. So it's a bit darker red here in the lower left corner, but I mean, everything else is also important. So this led us to, like developing a new method where we combine this self-explaining model with layer-wise relevance propagation. So one of this model-aware explanation method. And we published this in the paper. This looks more like that. I don't want to tell much more about this because later on, Shruti will do this in a poster presentation. It's a poster with the number 28. And this should be just a small teaser with the result that using our, let's say, extensive method of the ProFiL, there you can then really see that the explanation is more precise. So the explanation for this image, why this image is classified as a horse, it is really based on the text and not the horse itself, the prediction. So this is why a clever Hans was learned. Okay, so this is why I would call it as a fourth category, like we can combine SCI methods. We can combine, for instance, self-explaining models with model-aware methods. Okay, then another category are global explainable methods. Just to understand, for instance, global explanation, there's one method called activation maximization, and I want to shortly show you how this works because I really like the outcomes of this method. And I guess most of you have seen those little crazy images. Okay, so how does it work? We have an input here, right? So it's an image of a boat. And we have some kind of network here, and the network say, okay, it's a boat. Great. Okay. So how can we get now global explainability out of this? So we want to see, for instance, what the networks has learned for the class boat, like what concept has the network learned. And this is why we now go ahead and start with some random image, right? So just, a random image here. And we now don't want to optimize the network itself. We want to optimize an image that maximally activate this output neuron of a class boat. And by doing this is what we get. So this is like the activation maximization of the class boat. And we can really see that, okay, this concept of a boat was learned by the model. And also it was learned that a boat is most of the time on the water. So we can see here like water patterns. And we can also maybe it's some mountains behind. Okay, so this is what global explanation is. So we don't want to explain a certain image, but we want to more get an intuition about what the network sees. Okay, and just for instance here, in order, because I really fan of this Clever Hans, because it's so important that we detect Clever Hans as like this watermark. And I was interested in the question, can we even find the Clever Hans information in the global explanation? And therefore we have an image without the Clever Hans, so without the text information, and one with. And then we check in the different layers. So these are like the layer names. What neurons are activated the most by those two images? And how do these neurons look like? So, and those two images in the first layers activated maximally the same neurons, okay? So it's like you feed in the image and you just look like which neuron in this layer is activated the most. And this, then we plot, we make this global explainability method to see what the neuron has learned. And we see there's no Clever Hans activation. And in the later layer, we see, okay, those both images maximally activate different neurons. So the first without the watermark is, we also here have no clue. So there's like no watermark, but the image with the watermark activated maximally those neurons here. And you can, so at least I can, I hope you too, like see or imagine that those are like text patterns that the network has learned, right? So with global explanation, we are also able to figure out neurons that are like, let's say, not manipulated, but learned the artifact. I find this super interesting. Okay, and what else we can do? Again, combining explainability methods. So here we feed the horse class visualization, so the global explainability of the output neuron of the class horse, again in the network, just and then we applied local explainability methods, just model aware methods, in order to check what were the most important parts of this global explanation for the model to classify it as a horse. So maybe this was too complicated now. Okay, so first I made here a global explanation for the class horse. And this is like the global explanation. Okay, and I take this and feed it again into the network, just to know how is it classified. Of course, as class horse, because it maximally activated the output neuron of the class horse. And then I wanted to know which areas in this image were the most important for classifying it as a horse. So where it may be the horse, or are it more like this patterns here, this text patterns. And indeed, like different integrated gradients, guided gradcam, are like showing now the areas that lead the model to classify this as a horse. And we see it's not the horse, it's really more the text patterns. And this is, I think this is super nice to know. Okay, so now we make a jump, because my topic was in the first place telling you why or how Bayesian neural networks can help to improve explainable AI. So this is why before now you get a small intuition about what for different methods we have, what for challenges do we have with the different artifacts, for instance. Okay, so, and now the running example will be this image here. This is an image from ImageNet, and it's showing a castle, and castle is also one of the 1000 classes of ImageNet. And yeah, the image is correctly classified as a castle by a model we took. And when we now apply an explanation method, we see why this image is classified as a castle. Because the castle was important, but also we see that, so red stands for important, for classifying this as a class, as a castle. And blue areas mean, okay, this was not important, or even this was against the class castle. And we see that not only the class castle, the castle is highlighted, but also this lamppost over here, right? So this lantern, and also the cars and a bit of the street. And there we wonder, maybe we can get now, with help of some Bayesian neural network information, with some uncertainty information, the areas where the model is more certain about that this is belonging to the class castle, and maybe the areas don't have red color anymore, that are not so important for the model to classify this as the class castle. Okay, so Bayesian neural network can help here. How? So this is a normal neural network. So you see, like, we have connections between each of the neurons, and we learn just one weight. For a Bayesian neural network, instead, we learn a whole distribution for each of the connection between neurons. So this is a normal neural network. You see, we learn just a single weights, and here, for the Bayesian version, we learn the distributions. And of course, what we can do now from a distribution, we can sample, right? We can sample once. So here, just per accident, we sample the same numbers of the normal neural network, but we can sample again, and we get different numbers for the connection between our neurons. And this we can do multiple times. And this is because, yeah, what we have learned here is called the posterior distribution, okay? So the distribution over our weights based on our training data. Okay, so what can we do now with this? So given here some input image of a cat, we feed it into our Bayesian neural network. In order to now get a prediction, we sample several times. So we sample here n times, a new network, okay? So like this year, we sample this, let's say 1,000 times, so really often. And for each sample of our Bayesian neural network, we can feed in our input image, and we can get a prediction. So this means doing this 1,000 times, n times, we get 1,000 different predictions for the same input image. And now we can, of course, aggregate our predictions. So for instance, we can compute the mean prediction, but we can also compute the variance of the prediction, which would give us an uncertainty estimation of the prediction of the model. And yeah, for instance, when the network, let's stay with this cat here. I mean, we can also go into a medical example, but we would trust the model more, I guess, when the model, like, say, okay, this is a cat and I'm with an uncertainty estimation. So when 99% of all the Bayesian subnetworks, so the Bayesian instances here, say that it's a cat, right? And we wouldn't maybe trust the model or the prediction so much when, let's say, only 60% of the models say it's a cat, and there are like a lot of other models say it's a dog or it's a human or it's a tree. So this uncertainty estimation helps us a lot in order also to gain a bit of more trust into the model outcome. And now we wanted to transfer this uncertainty estimation information also into our explanations. So of course, we can compute an explanation for each prediction regarding each subnetwork or each Bayesian neural network instance. Okay, we just take the prediction and, for instance, make a model-aware explanation method and take the prediction, backpropagate it through the model until the input image is reached. And there we see for each Bayesian neural network instance, we get a different explanation. And now, again, we can compute, for instance, the mean explanation. Or we can compute the union and intersection. So, you know, the intersection would be then where all networks agree on that this is an important area, and we see this is the head where everyone agrees on. Or we can also compute the union. Okay, and yeah, we could also cluster it. So now again, our running example, we have our castle over here. This is like the standard explanation. And when we do it now in a Bayesian way, here, for instance, we have 5 different network samples. And we see we have 5 different explanations. And we scale it up, of course. We have here 100 or 1000 different explanations. And then we can compute the intersection. So we see like where we take 95% of the networks agree on which area. And we see it's indeed the castle where the networks agrees on, and not the lamppost anymore. And also here some parts of the streets are not important anymore. And if we compute the union explanation, so like taking into account all the information of the different Bayesian neural network, we see like there are a lot of different areas that plays a role in the prediction of the class castle for all the different networks. Okay, so we tried this on different data sets, and here we can see an image of a cat. Here is the intersection explanation and the average explanation. And then and the union one. And then we gathered all the information into one image, into one explanation, which we called UAI plus explanation. And these are the different percentile information. So for instance, you can think about the intersection explanation like the 95 percentile, no, sorry, the small percentile, so like the 5th percentile explanation, meaning that 95% of the networks agree that this area is important. And when we increase the percentiles, so for the union, for instance, we have the 95th percentile, meaning only 5% of the networks needs to agree on a certain area. And here we collect all the different percentile information into one image, such that we can directly see, okay, red is the eyes and the nose were the most important areas. So the model based its prediction on in most of the cases, and the blue areas are less important, or the model is more uncertain that those areas play a role in the prediction of the class cat. So then we had some histopathological data. Here you see an input with annotated cancer cells. So the black dots were made by an expert later on, but the model didn't get that information. It's just for us to check if our model and our explanation method find the right area, or let's say the model predicts its decision on the right areas on the cancer cells. Let's jump directly to the UAI plus explanation. So we see that the most important areas here in red are mostly indeed like the cancer cells. And and this is like also a huge challenge in explainable AI, because like the model, as you can see here, found also some cancer cells which are not highlighted by the expert. So meaning now here's the huge question, like maybe the model just, made something wrong, detect wrong cancer cells, wrong areas as malicious, or the expert just, forgot some or didn't realize that there are more cancer cells in this image. Okay, again, back to our Clever Hans examples. So what we can now really say with our UAI plus method is that indeed the Clever Hans was the most important, or one of the most important areas for the model to decide that this is an image of a class horse. Okay, and also, as you can see here, you can think of this then as a clever Hans too, that the tree were important for the model to decide that this is a horse. Because why is this? Of course, then there were a lot of images of horses with trees in the background. Okay, so jumping now to also, it's also in the way of uncertainty, but not Bayesian neural networks anymore. But it's about how uncertainty can also help here. So let's focus on this image. So we have here different input images, and here we have our explanation, and this is now just the absolute gradient explanation. And we see that we call it a gradient shattering effect, because you see it's a lot of noisy outside of the object here, a lot of noise. And the question is, how can we handle this noisy gradient shattering effect? And so this is like, we have here our input image, feed it into our black box, into our model, and we get an explanation, right? So this is like the normal way you do it. And then there's a method called smoothgrad developed by Bean Kim. And what they do is they reduce this gradient shattering effect by adding more noise. Let's see how this works. So they have their input image and they just add some Gaussian noise, so some tiny noise to the input image, and then they feed all these noisy versions into the model. And then, of course, for each noisy version, they get an explanation. And afterward, they take they just average over all this noisy explanation and get the final explanation. And here are the results from their paper called smoothgrad, removing noise by adding noise. Here is the noise level at the top. So 0% noise is added. So it's like the normal absolute gradient explanation. And then they add 5% noise to the input image for maybe 100 images. And then this is the average explanation. And we see that with an increasing noise level, for instance, here, noise level of 10 and 20%, the explanation gets clearer, right? So the gradient shattering effect in the back is reduced and the object is more clear. Here it's you see it very clear. But then, of course, after some kind of threshold, after you increase the noise level more than 20%, you see it's getting worse again, and there's you don't see any more meaningful. So there's like this sweet spot of adding noise between 10 and 20%. So, and there's now this method NoiseGrad. What we developed very recently is because of this, with the idea of the Bayesian neural network in mind, where not the model stays the same because you can sample and you can have a lot of different versions of your model. We don't touch our input image, but we put the noise instead of to the input image, like smoothgrad is doing. We put the noise to the weights in the model, okay? And by each time adding different noise to the original trained model, we get different versions of our model. And we feed then our input image in all the different models and get, of course, then again, for each different model, we get a different explanation, and then we can average the explanations. And and then we came up also with FusionGrad, which is just a combination then of smoothgrad and NoiseGrad. And we put noise to the input, as smoothgrad is doing, and also noise to the models. Okay. So this is a toy example, like what is going on here, like the baseline explanation, for instance, is here just the gradient. So we have, let's start with this. So we have two classes, like the orange class and the blue class, and these are the decision boundaries learned by the model. And now taking just one random point here, this would be just the baseline explanation, just the gradient. And for smooth grad, it would be now the case that we put noise to this input point and compute for all the noisy versions of the input the explanation. So, and you see the different gradients of the noisy inputs, and then we would take the average. In our case, for noise grad, we put noise to the model itself, right? You see this here with the different decision boundaries. And so we also get different gradients based on the decision boundaries. And for fusion grad, it is both, okay? The different noisy versions of the input and the decision boundaries. Okay, so to show one result, we have here the image. Here is the baseline explanation. The smooth grad explanation, you see, okay, the dog, the shape is getting more clearer. Also here. And for the noise grad, you see that now also the eyes were found by the explainability method and also the nose, which was not the case for smooth grad. And yeah, and for fusion grad, you see that the shape is, okay, there you see also the eyes are not there, not detected anymore by the explanation method, because now we make the combination. But what you see is that the shape is getting much more precise and clearer. Okay, so yes, we can split our explanation methods in local and global, and we also learned the different categories of the explanation method. And yeah, this we already had, right? You remember that we can compute a global explanation. And I now just want to show you in the last slides that how using uncertainties can also improve on global explanations. Okay, so this is a global explanation of what is the question. So maybe you can see it. So me in the first place, I couldn't see which classes might have been, but when we now apply noise grad to this, so like not just optimizing one output, but optimizing like all of, let's say, 100 different subnetworks, samples from the Bayesian neural network, the output of them at once, this is what we get. And here we can extract that, okay, the class is, it's a pug dog. Another example, this is a Persian cat. And we can also see that, yeah, it's using noise grad, like using Bayesian neural network information here, or let's say it's not directly Bayesian, but it's like using uncertainty information can increase the preciseness of the global explanations. Okay, other examples are the pelican. You can better see or extract that it's a pelican, and also here's a jellyfish. Yes, and that's it from my side for now. Thanks for your attention, and I hope you got a bit of the intuition about explainable AI and the challenges and how you may improve your explainability by using Bayesian neural networks information. Thank you.